Hey everyone, this is Aanshul Sadaria, Software Engineer 3 at Google. In the past, we have done so many system design related videos like we did for Twitter, we did for Tinder. It's always amazing to see how large scale products like this work. In this video as well, I'm going to cover the system design of one such large scale product. Day to day for commute, we use this application on a regular basis. Yes, you guessed it right. We are going to cover the system design for Uber. Now, when I say Uber, I also mean Ola, Lyft, Careem, and all of those applications which are used to provide us cab services. But before we dive deep into the video, make sure you check out Scalar's free masterclasses by industry leading experts only on Scalar's event page. Link is in the description below. Now, let's get started. Now, before we start the system design of any application, the first step is to understand the customer user journeys, which is how the customer would interact with that particular product or application. In this case, we have two different types of customers, a normal user or a rider and a driver. Let's try and understand what all different customer user journeys will be there. Now, we will refer to customer user journeys as CUJs. Let's first try to note down how a driver will behave with the application. They will first create their profile. Then they will show their availability on the application that, okay, hey, I am available to take the rides. Please give me rides if they are available in the nearby location. Next, they have an option to accept or reject the ride whenever they get a notification that, okay, some user in the nearby location is asking for a cab service. So, accept or reject a ride. Now, when they reject the ride, they are back to square zero and the same flow repeats over and over again. But now, if they have accepted the location, they will be able to navigate to the location, that is the pickup location of the particular user. So, navigate to pickup location. Now, once they have navigated to the pickup location, they are given an option to start the ride. They have accepted the ride. Now, they will start the ride as soon as the person gives the OTP or any such authentication mechanism. So, start the ride. As soon as they start the ride, the user would have mentioned some pickup location and some drop location. So, the navigation towards the drop location begins after the ride has started. So, navigate to drop location. Once they have navigated to the drop location, the driver can end the ride and accept the payment. Now, optionally, we can also give them the facility to rate the particular rider as well, and the same facility will be provided to the rider as well to rate the driver. Now, this is an optional requirement. We can add it if we want to. Let's try to see what all are the customer user journeys for a rider. Same thing, they will also create their profile. Now, based on the location of the rider, it will show them what all cabs are there in the nearby. Like if you have opened the Uber application, whenever you open the application based on your current location, it will show some cabs which are available in the vicinity. So, show cabs nearby. Now, I will be given an option to put in the start location and the end location for the cab service. So, add start / end location. Now, based on the start and end location that I have put in, I will be shown the estimated time required to reach the location, which is the end location. And I will also be shown the approximate price of whatever the cab service is going to be. You know, it's not the exact price, but it also gives an estimation that, okay, if Uber Moto, it's this particular price, Uber Auto, it's this price, and so on. So it gives an estimation of what the price could be. More likely the price is going to remain the same, but depending upon the traffic condition, or maybe the driver needed to change the route because of any obstruction, the price may increase or decrease. So show ETA and approximate price. Now, once it shows the approximate ETA and the price for the cab service, what the application will do is it will start finding the cabs for the particular person. So book cab is one user journey for that. Like right now we have not started to book the cab, we are just seeing what all prices are there, what all timing it's going to take and so on. So book cab from the start location to the end location is the next user journey, and then the remaining user journeys are on the part of the driver. So once the driver accepts the ride, the driver will navigate to the user and the user will sit in the cab, the driver will start the trip, the driver himself or herself is going to navigate to the end location and then drop the user. Lastly, the user is going to make the payment and rate the driver. So that is also an optional requirement, but let's add make payment over here. So now these are the customer user journeys on the side of both driver and the rider. Now one important or one customer journey which we have not added in the typical flow is the ability to see the past trips or the payment history. So that is something we can add over here as well. Let's just change the color. So see past trips. Now this can be done on the side of both rider and the driver. And similarly, you can see your current trip as well, because a lot of time it happens that, okay, 10 minutes the driver is going to come in and we keep on looking at the trip status, or we keep on looking at the current trip. So we can either look at the past trips, get a particular trip, like if we want to get information of a particular past trip also, we can get information about a past trip. So get a past trip or get current trip status. Now the benefit of understanding all of these customer user journeys is that each of these customer user journeys get translated into a functional requirement. Like these are the functionalities that the app should provide. Now we have understood some of the functional requirements. Now when I talk about customer user journeys or functional requirements, I mean one and the same thing. All the customer user journeys are going to be mapped to some sort of a functional requirement. Now let's take a look at some non-functional requirements as well. When I say non-functional requirements, which I have covered in detail in Twitter's system design as well, what I mean by non-functional requirements. Now this doesn't typically affect the customer user journey, but it affects the user experience. For example, if it takes a lot of time for you to check the current trip status, then it's a bad user experience. So that is a part of non-functional requirements, that the latency should be as minimal as possible and so on. So let's take a note of some of these non-functional requirements as well. Now we talked about the first non-functional requirements, which is minimal latency. Now when I talk about minimal latency, it's not that I want super low latency like that which is required for high frequency trading firms. I am fine with some sort of a delay. Some of the services, for example, if I'm making a payment, it's fine if it takes a bit of time for the payment to get through, or if I want to check some of the past trips, it's okay if it takes some time to show me the list of past trips as well. But some of the customer user journeys should have as less latency as possible. Now the next one would be highly available. Now it is not possible to imagine if Uber is down in a city like Bangalore or Mumbai or Delhi and so on. So it needs to be as available as possible, and I'm just talking about India over here. In US and all the countries around India as well, it is very, very important that services like Uber stay highly available 24/7. So highly available is an important non-functional requirement. Now the next one would be durable. When I say durable, I mean the data should persist forever. For example, let's say that a driver is taking 10 trips in a day, and at the end of the day, the entire trip record for the day is vanished altogether. Or for example, if I have made a payment to the driver and it still shows that, okay, the payment is not done through even after 3 to 4 days, that payment history is gone altogether. So such an experience is not expected from applications like Uber. The data should persist forever, be it trip history, be it location data of the driver, or be it the payment history or anything at all. The information should be durable in the database. Now the next one will be, it should be highly scalable. Highly scalable because every day there are some peak hours and non-peak hours. So if the system is not able to scale to the peak hours, for example 9 a.m. in the morning or 5 p.m., 5 to 7 p.m. in the evening, then the user experience will be really bad. And if we want to add the service to new cities, to more tier 2 cities, tier 3 cities and so on, the application should easily be able to scale to such an extent that we are able to cover almost all the cities of the world. So it should be highly scalable as well. And lastly, it should be highly consistent, or let me put it into better technical words, it should be strongly consistent. Now you must be wondering that we want our service to be highly available as well, and we also want it to be strongly consistent. Now CAP theorem says that one service cannot be highly available and strongly consistent both at the same time. Now that is absolutely true, but here's the catch in this. We don't want the same features or same set of microservices to be both highly available and strongly consistent. For example, if there is a cab finder service, we want it to be highly available. We don't want that to go down at all. But for example, if there is a trip service or a payment service where I want to check some of the past payments, or if the payment has gone through or not, we don't want that to be strongly consistent. We are fine with eventual consistency for such microservices. It's all right if I made the payment through and it takes 5 minutes, 10 minutes for the payment to get reflected in my application. But on the other hand, let's say I have booked a cab and some driver has accepted that particular ride. I cannot accept the experience where other drivers are still being shown that, okay, this person is still asking for a cab. So in such situations, strong consistency is really required. And also, for example, if I start the trip and it still doesn't show that the trip has started on the driver's application, then that's also a really bad user experience. So all of these things, some of these features need to be strongly consistent, whereas some features we are fine with eventual consistency. So the set of features which are highly available and strongly consistent, they are mutually exclusive and they don't overlap. So this is the set of non-functional requirements which our application must be having. Now, from the non-functional requirements, let's try and understand the scale at which an application like Uber works. Okay, let's just crunch some numbers so that we have an understanding of what the read QPS can be, what the write QPS can be, and so on. So, first of all, like I am following the data which was published by Uber's blog, Uber's website itself. So, it's a public data and I'm not making the numbers up. Now, it was seen that there are almost 100 million monthly active users. 100 million MAU, which is monthly active users, which means that over the duration of 30-31 days, there are almost 100 million active users. So on a daily basis, you can expect to have around 10 million rides. So there are 10 million rides daily. Rides per day. Now we will try and compute the QPS based on the number of rides in a day. Let's just wait for a second for this particular thing. And another number, like all across the globe, we can expect around 1 million drivers to be active on a daily basis. Since there are 10 million rides in a day, we can assume that one driver typically has 5 to 10 rides in a day. So ideally, there would be 1 million drivers active on a day-to-day basis. Now, when we say 10 million rides in a day, what does it mean? Per second, how many rides are getting booked or how many rides are getting requested? Let's do some computation for the same. Now, in a day, there are 86,400 seconds. Now I am going to assume this to be 1 lakh seconds just for the sake of computational ease. So now 10 raised to 7 million rides divided by 10 raised to 5. Now this is almost equal to 100 rides getting requested or booked per second. Now this is a huge load because behind the scenes, whenever a cab is booked, a lot goes behind the scene. A radius is created around the user's location and the application tries to identify what all cars are there or what all cabs are there in that particular location. Pings are sent to all those drivers in that particular radius and then a ride is booked. So 100 QPS is our load, operational load, and we will cover some of these aspects, like what is the purpose of having 1 million drivers in a day or 100 million monthly active users. We'll try and understand how it is going to influence the system design of Uber when I'm going to talk about some of the important tech concepts. Now let's get started with some of the tech concepts which I feel are really crucial in order to understand the overall system design of Uber. Starting with the most basic one, like how is the driver and the rider being able to communicate with the Uber servers. So I'll just create a superficial diagram of this. Now when I say rider or user, I mean one and the same thing, so I might use these terms interchangeably during the course of the video. Now ideally both the driver and rider are going to communicate with each other only via the server. Now there are two ways of communication. The first one is the synchronous way of communication using HTTP request. So what does HTTP request mean? You send a request for some data and you receive a response in return. So the first one is HTTP means of communication, or HTTP protocol as we popularly know it as. So you send a request and you receive some response in return. Now let's say, for example, the rider wants to request a cab from the Uber application. So it sends an HTTP request to the server saying that, hey, I am at this particular latitude and longitude, or I am at this particular location. Please send me an Uber. Now when I say book an Uber for me, I mean Uber Go, Auto, Moto, or anything at all. We are not going to differentiate between these different modes of cab services. We are going to treat them as the same thing. If we want to include different types of cab services possible on an application, it's a plug and play thing. It's not a big deal for the purpose of this system design video. So we are not going to treat them as a different thing. When I say Uber or a cab service, I mean one and the same thing. Alright, so now the server knows, now the application knows that, hey, I want to book a cab for this particular rider located at a particular location. Now how does it communicate with the drivers? Does it send all the drivers an HTTP request requesting for their particular location? Like the server would ping all the drivers and ask them that, okay, let me know what your locations are, and then based on the locations and the nearby vicinity, it will send the possibility or suggestion for a cab request to those few drivers only. This is one way in which we can perform the communication between the driver and the server, but as we know, this is an inefficient way of communication. The other way of communication is using WebSocket servers. Now what does WebSocket servers mean? When we create a WebSocket server, it creates an open connection between two clients. Now in HTTP there is a concept of client and server. Whereas when we talk about WebSocket connections or socket connections, there is a P2P connection, peer-to-peer. There is no discrimination between client or the server. So this is a P2P connection. Both the peers can send each other messages asynchronously. So HTTP was a synchronous way of communication, and WebSocket connection is a peer-to-peer or a asynchronous way of connection. So this is asynchronous and HTTP is synchronous. Now using the WebSocket servers, what the drivers can do is they can keep on sending the location pings to the server on a regular basis. It can be every 4 seconds, 5 seconds, or 10 seconds. It depends on what right QPS is sufficient for our particular use case. So now let's try and understand how the WebSocket connection is created. So let's consider a server sitting over here and a user sitting at the other end. Now when I say user here, I mean both the driver and the rider. I don't mind discriminating between them as well. So this is a socket connection created between them. So let's say whenever a driver becomes available, it sends a ping to the server saying, hey, I am available, and then it immediately creates a WebSocket connection between the server and the client. So the server knows that, okay, this is some connection ID. We will also have a connection ID. And this connection ID corresponds to this particular user ID. Now this user can be a driver as well as a rider. So now the server knows the link between a connection ID and a user ID as well. Now for the user only knows what connection ID it needs to put the message on. As soon as the message is put on that particular connection, it travels to the server and identifies what the request is or what the message is. It can be both a request and a message. A message can be just a location ping for some driver that, hey, I am at this particular location. Whereas a request can be, I am accepting a ride or I am rejecting a ride. So in this way, the WebSocket servers make the communication between two different clients or two different peers efficient. So for the use case of an Uber application, we are going to use WebSocket servers, which is going to establish a connection between the riders and the server, as well as the driver and the server, so that the messages keep on transmitting between all the parties. Now we understood how the communication in an Uber-like system behaves. Now let's move on to the next technical concepts and see how we can find cabs nearby a user who is requesting for a cab service. So now let's just create a table for the location data based on which we are going to find the nearby cab drivers. So there is going to be some sort of an ID related to the driver, and we are going to store both the latitudes and longitudes. Now in between, I just might shift from latitude longitude to XY axis. So I really hope you try and understand that by XY also I mean the latitude longitude thing. So now let's assume we have a table in which we are storing the latest location data of the drivers. I'm going to explain in detail how we are going to do that as well. But for the time being, hypothetically, let's assume we have some sort of a database, a fast retrieval database from which we can access the latitudes and longitudes of the drivers. Now we know for a case that there are 1 million active drivers in a day. Okay. So at any moment when we are going to find the nearby drivers, we can assume that estimation to be correct as well. So let's say this is the map of the world. Okay, I'm just going to draw a rectangular diagram, and this is the map of the world, and the user is located at some point over here. So now ideally we want to find the drivers in a nearby radius of a few kilometers, 1 kilometer to 5 kilometers and so on. So what the naive way, the most trivial way in which we can do this is by iterating through all the, like this entire table, location table. We can iterate through the entire location table and try to identify the drivers who are near me. Now another important thing to keep in mind is that we were having a QPS of 100 for cab search. So now if the QPS is 100 and we are going to traverse through the entire table of 1 million drivers, it is not going to be efficient. So one way in which we can get some improvement in the performance is by creating index over latitude or longitude. We obviously cannot create a primary index on both of these dimensions. So let's say we create a primary index on latitude. So for example, now over here we can assume that the latitude and longitude is x and y. Okay, so nearby the x latitude we want x minus 2 to x plus 2. This is the range in which we want to find the drivers. Now even after we have optimized based on one particular index, it is going to be a lot more inefficient, because there could be, in some cases, there could be a lot of drivers in a particular range of latitude or longitude as well. Another way to get more optimization, to try and improve the efficiency even further, is by creating two different databases with a primary index. In one table we can have a primary index on latitudes, and on one table we can have a primary index on longitude. Now based on those primary indices, we can find all the drivers who are in that range of latitude and in that range of longitude. So ideally we will find a pool of drivers which belong to this particular latitude range, and we will find some drivers belonging to this pool of longitude range. Now after finding those drivers, we need to find the intersection between both the sets. Now this too, with a QPS as high as 100, it's going to be very, very inefficient. So we need a way in which we can convert this two-dimensional data into one-dimensional data. So for this purpose, I covered some of those topics when we discussed the system design video for Tinder. So do go and take a look. I'm going to mention some of the ways in which we can perform this particular thing, wherein we convert the two-dimensional data to 1D data, one-dimensional data. Now the first such way is by using geohash. I'm not going to cover in detail what geohash means, but basically the entire world's map is divided into chunks, and each of this chunk corresponds to some particular geohash. Now another way to do this particular thing is using quad trees. Now quad trees is also something which I talked about in Tinder's system design video, and if you want me to cover this in detail, then I can also prepare a system design video on Google Maps system design. Like, you can add it in the comment section if you want me to prepare a system design video for Google Maps as well, where I can cover all of these topics in much more detail. Now, what Uber actually uses in its backend for the map service in order to identify where a particular driver is, or in order to find the ETA between two different points, and also for the navigation purpose, it's the Google S2 library. Now what Google S2 library does is also similar to, somewhat similar to what geohashing and quad tree does. It divides the entire spherical globe, which is sort of a three-dimensional data, into chunks. Now over here I have, just for the sake of clarity, for the ease of explanation, I have just created a rectangular map and I have distributed the entire map into smaller chunks. So now each of these chunks is some form of a one-dimensional data. We can just name each of these chunks, we can just order each of these chunks. For example, this can be chunk, the ID of the chunk can be 1, this is 2, 3, 4, 5, 6 and so on. So in this way we have categorized the entire spherical data into one-dimensional data. So we converted the two-dimensional data, which was causing us an issue during the driver fetch, by converting into one-dimensional data. Now whenever a user is pinging from a particular location, okay, we know the latitude and longitude of the user. Now each of the latitude and longitude is going to be part of some particular chunk. Let's say it's part of chunk 5. Okay, so now we ideally want to find the drivers who are in that particular chunk or in the chunks nearby it. So now this is the responsibility of the map service, that hey, given this latitude and longitude, let me know what chunk does the user belong to. Now this user can be both rider and the driver. So when we put in the latitude and longitude to the map service, it tells us that okay, this particular user belongs to chunk 5, and then what the map service does is, based on a user's location, it will create a radius around the user's location. It can be a 2-kilometer radius, which will have a 4-kilometer diameter, or any XYZ particular radius. Okay, now based on this radius, it will cover a set of some chunks. We will get what all chunks are part of the subset in which we want to find the drivers from. So over here we can see that chunk IDs 1 to 9 is the search space wherein we want to find the riders, wherein we want to find the drivers, my bad. So ideally we will also have a service which will store that in a particular chunk C, what all drivers are there. So we can directly communicate with those drivers and send them a ping that hey, a user is requesting for this service, do you want to accept the ride or not. So in this way we just find what chunk does the user belong to, and based on the nearby chunks we send the ping to the drivers who are in the vicinity of the user. Now what we have done is we have isolated the maps microservice, which is responsible for converting the pair of latitude and longitude or the XY dimensions into the chunk ID. So let's keep making a note of what each of the microservices are doing. So map service, it's going to convert a pair of latitude and longitude to chunk ID. Now this map service itself has dissected the entire map into different chunks. So based on the chunk ID of the user, it can identify what all different chunks are there nearby. And we talked about some service. Let's keep it a question mark service over here. We will name it ahead, like I will talk about that service in detail in the coming section. So now what this does is it has a mapping from chunk ID to the set of drivers who belong to that particular chunk. Now ideally, using that map service, what we have done is we have reduced the search space of the drivers to whom we want to send the pings, that hey, there is a user do you want to accept the ride for that particular user or not. So now let's try and understand what all different things the map service can do. First of all, the ETA computation. Let me also create the map of a city to explain it in a better way. Now this is just a map of some city. I am going to divide the map into smaller chunks, which is what the map service or the Google S2 service is going to do. Now these are the chunks. Let's say the user belongs to this location, and Google S2 service, Google S2 library is going to create a radius around it to find what all chunks the other drivers are in. Now let's say we found some drivers in the nearby chunks. There is a driver located over here, 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 here and here. Okay, we found out 4 drivers in the nearby chunks based on the radius that we set and the user's location. Now we want to find the ETA, that okay, given a start point and an end point, what is the ETA for, first of all, what is the ETA for the driver to reach to the pickup location, and ultimately what is going to be the ETA to reach the destination. So now based on the chunk IDs, if you remember, we also had a location table which contained the latest locations of each of the drivers. So now if we have isolated 4 driver IDs or 4 user IDs who are in the probability radius, then it is easy to get the exact locations, exact latest locations of each of these 4 drivers. Now based on those locations, we have 2 choices with us. First of all is just to compute the distance, which is the Euclidean distance based on a set of 2 different points, but that might not be the ideal distance, because we know that for any in a city between point A and point B, we follow a road-like structure. So the distance is, if the aerial distance is 1 kilometer, then the actual distance might be something else altogether. So this can be a 3 kilometer road distance. So we cannot rely on the radial distance, we cannot rely on the aerial distance as well. What we'll do is we will use the map service, which is the Google Map service or any map service which is feasible for the particular application, and then based on that map service we will just let it know that okay, this is the driver location and this is the user location. We have isolated some drivers around and we have their locations. Let us know what the ETA is for the driver to reach the user. Now based on that, we will just compute what the distance might be for each of the drivers and what the ETA will be for the driver to pick the user up. Now that is added to the ETA for the pickup location to the drop location. So in this way, we can compute the ETA. Now this ETA, or ultimately what we are doing is we are finding the distance, probabilistic distance, and the time taken to cover that distance. Now both of these things can be passed on to the payment service, which will then calculate what can be the estimated price for that particular ride. So in this way, in collaboration with the map service, we will get the locations using the location service. We will use the payment service as well to compute the ETA and also to compute the estimated or approximate price. Now let's see, for example, if a driver is moving, the driver will keep on sending the location pings to the server. So how is it going to affect the flow? For example, the driver is situated in chunk 1, for example. All right. Now let's say the driver is moving in the right direction. So at some point the driver is going to change the chunk ID, or he or she is going to change the chunk in the map. Okay. So let's say this chunk is chunk 2. Now on a regular basis, the updated location pings of the driver are sent to the server, and what the server will do is that it will use the map service, and inside the map service the Google S2 library will let us know that okay, this is the latest location, and as per the latest location either the chunk ID has changed or it has not changed. And if the chunk ID has changed, let's say for example it was 1 earlier and it changed to 2. If you remember, we had a question mark service, right? So that question mark service, it will have that okay, earlier the chunk ID had driver D1, but now since the chunk has changed, we will get rid of the driver 1 from chunk ID 1 and then we will move the driver to chunk ID. Now let's say the chunk ID earlier was 1 and then based on the location change we got to know from the map service that okay, now based on the latest latitude and longitude pair, the chunk ID is 2. So ideally, if you remember, there was a question mark service. Okay, let me name it right now. It can be the dispatch service or the cab finder service. Let's call it the cab finder service, because it keeps the note of what all drivers are belonging to a particular chunk ID. So earlier, driver D1 belonged to chunk ID 1, and as soon as the location changed based on the information we retrieved from the map service, we will remove D1 from chunk ID 1, and then it will add it to chunk ID 2. Now we will understand the cab finder service in a lot more detail, but this is what I wanted to explain, that okay, this is how the user or the driver keeps on sending the location pings to the server. Based on the location pings that we are getting from the driver, the map service will identify that okay, this is the chunk ID which it belongs to. So now let's start categorizing what all different services we have discussed till now. First one is the map service. The map service is responsible for converting the lat long to the chunks it belongs to. It also performs the calculations from point A to point B, that okay, this can be the potential route, this can be the approximate time taken to reach the destination, this is the approximate price which will be required for the cab service. So these all things are done by the map service. Now we kept on talking about receiving the location pings, so let's try and cover the location service in detail as well. So the location service is responsible for all the location data related to the user as well as the driver. Like user, I mean the rider. So let's say there is a driver, and let's continue this discussion only for the driver, because the driver is continuously going to send the location pings to the server. And what the server will do, what the location service will do, is that it will store the latest data into the table. Now we will have a table, as we discussed earlier, which will contain the driver ID or the user ID, and it will also contain the lat and long of the particular driver. Along with this, we also want the entire history of the location pings that the driver or the user has been sending to us. Why do we need it? We potentially might be needing it because we want to perform some machine learning thing, or we want to perform some analysis on top of it. Let's say a trip has ended and the rider has challenged that okay, the driver took a bad route and that is the reason why the price has increased and I don't accept this particular price or this particular fare. So what the application will do in the backend is that it will check the entire location history and identify if this was the optimal route suggested by the map service or not, and then based on it, it will retrace the entire trip and identify if there was any mishappening which happened during the particular trip. So there are a lot of use cases, and for the safety we are going to store the entire location data for both the users and the driver. Now naturally, if we are going to store the latitude, longitude and the user ID, let's do some calculations to see how much data is it going to store. So for the user ID, it is going to be 8 bytes, 64-bit. Now for latitude and longitude also, let us assume it's going to be 3 bytes itself. So one row for one driver, it's going to consume 24 bytes, or for the ease, let's consider it 25 bytes for the computational ease. Now there are 1 million drivers who are active every day. So the entire capacity of the table is going to be 25 times 1 million bytes. Now this is going to be 25,000 kilobytes, and which is equivalent to 25 megabytes. Now 25 MB is quite small as compared to what all resource capacities we have nowadays. So this entire table can be stored in a Redis cluster in the form of a cache, so that the retrieval is fast. Whereas when we talk about the entire location history of any user, it's going to consume a lot more data, and this data is going to grow along with time. So it doesn't make sense to store it in the form of a SQL database. So that data is going to be stored in a NoSQL cluster or a Cassandra database. So we have two things. The location service is going to hold the latest location data, and we are also going to store the historical location data. Now this is going to be stored in a Redis cluster for quicker access whenever we require it. Like the map service can require quicker access to the latest location of XYZ drivers. So location service will transmit that data to the map service or any other service which requires the location data. So location service is the source of truth. Whatever location we require for any user, they are going to ask the location service that, hey, this is the user ID, can you share me the latest location, or can you share me the historical location for this user? Now this is going to be stored in Cassandra. Now I hope it made sense why the table size motivated us to use a Redis cluster, and it also helped us to get faster access to the location data. Now let us just beautify this entire system design diagram for the ease of understanding, and then we'll talk in detail about the cab finder service. We started from the map service, we went down to how we are receiving the locations in the location service. Now we'll take one step back once again and try and understand when a user requests for a cab, what the entire flow looks like. So first of all, let me just make a better diagram. Now we know that the user communicates with the server through a WebSocket. So this is a WebSocket server, and in front of the WebSocket server we will have a layer of load balancing. Now why do we need load balancers? Because as we notice, there are 100 million monthly active users, and since these users are a lot, we are receiving 100 QPS of traffic from each of these users. So ideally we would want to balance the traffic amongst the WebSocket servers. So it's not just one WebSocket server. There is going to be a WebSocket manager who is going to handle all the traffic. The WebSocket manager will know that, okay, this particular connection ID belongs to this user ID, and this connection ID is catered by a particular WebSocket server. So we will have a layer of WebSocket servers. It's a distributed layer, and then behind this layer we will have a routing service. Now what this routing service will do is, based on the request, it will distribute the traffic between different services. We talked about map service. If there are constant pings of location data coming in, then it will go to the location service. If a user is requesting for a cab, it will go to the cab finder service, and so on. So right now we talked about map service, we talked about the location service, and now let's discuss in detail about the cab finder service. Now ideally what the cab finder service does is that it matches the demand created by the user and considers the supply of the drivers in that particular radius or among different chunks. So it tries to match the supply with the demand. So some people might also call it a dispatch optimizer, or the dispatch service, or the supply demand service. So I'm going to use more simpler terms and put it as cab finder service. Now let's go in detail and understand what the cab finder service is and how does it cater a request of a user requesting for a cab. Cab finder service. So whenever a request will come, it will look something like this. I have this user ID, this is my latitude, this is my longitude, go and perform the magic, right? So now this cab finder service calls the map service to identify what chunk it belongs to. Now the cab finder service looks something like a hash ring. I will explain in detail what the hash ring means as well. But to put it into simpler words, there is a distributed service where there are multiple servers. Each of this server is responsible for a set of chunk IDs. Okay, it doesn't matter what chunk ID is. For example, this is server 1, server 2, server 3, 4 and 5. Ideally, the number of chunks across the globe is going to be in the range of millions, if not billions. And I'm not sure, like it's going to be in the nearby order itself. But for the sake of clarity, let's just assume that the number of chunks is just 10, so that I can explain in detail what the cab finder service looks like. So each of these servers are associated with a set of chunk IDs. Now server 1 might be responsible for 1 and 2, 3, 4, 5, 6, 7, 8 and 9, 10. Okay, we have assigned the responsibility to each of these servers, and there is also a server optimizer or a manager of a sorts who is going to take control over what request is going to be sent to the server. Now this particular service leverages the benefits from consistent hashing. Consistent hashing. Now what consistent hashing means is, for example, we want to scale this service up because the number of chunk IDs increased. For example, let's say this is a chunk ID 5, and all of a sudden, you can say around 5 p.m. to 7 p.m., the traffic inside this chunk increased. So ideally what the Google S2 service will do is, it will break the chunk into multiple other chunks so as the traffic inside each of the chunks is almost in the similar range. We don't want bias to be there in any of the chunk IDs. So ideally, chunk ID 5 will get converted to something like 11, 12, 13 and 14. I'm just giving it random numbers. But what happened is, chunk ID 5 went off, and instead of it, 11, 12, 13 and 14 came in. Okay, probably we will leave the chunk ID 5 where it is, and we will just replace it with 14. So the number of chunks increased, and the responsibility for a particular server will also increase. For example, earlier it was the responsibility of server 3 to cater to the traffic belonging to the chunk ID 5. Now with the increase in the servers, it might be allocated to any of these servers. For example, we might assign the responsibility of 11, 12 and 13 in any random particular order. So what consistent hashing does is, whenever the scale increases, it is easier to add servers. Whenever the scale decreases, we can just get rid of some servers, because a bunch of chunk IDs might be merged into one. Okay. So hash ring has a structure of a ring, like that is the reason why we call it a hash ring. And it has some nodes on top of it. 1, 2, 11, 3, 4, 12, 5, 6, 13, 7, 8, 9 and 10. Now the entire concept of hash ring is in such a way that whatever chunks or whatever items are there before a particular server, it will cater traffic for that particular chunks. For example, between S5 and S1 there are 3 chunk IDs. So ideally it will be the responsibility for S1 to cater the traffic in those particular chunks, and the same like 3, 4 and 12 are there between S1 and S2. So S2 will be responsible for that. Now for example, let's say we want to get rid of some chunks, and ideally we will remove one of the servers. Okay, for example, we just removed S5. Okay, so what will happen? The hash ring will remain as it is. Now ideally S1, which earlier had only 1, 2 and 11, it will now also cater traffic for 9 and 10. So just by the removal of a particular server, it doesn't require a lot of changes. It obviously doesn't affect what happens to S4, S3 and S2. They can remain as they were, and the server manager, which we talked about earlier, they are notified that okay, now S1 is also catering the traffic for 9 and 10. Now there is another protocol which is used for this particular matching algorithm or cap finder service, which is known as gossip protocol. So whenever the responsibilities of any of the server changes, it will just gossip to the other servers that okay, now I have got more responsibility for chunk ID 9 and 10 as well. So if there are any requests for the particular chunk ID, do assign it to me. For example, in the earlier, let me just get rid of some of the clutter over here. So for example, if we receive a request from a user belonging to chunk ID 6, okay, so what the cap finder service do is, first of all, it will identify which server is catering to that particular chunk ID. So over here, it will identify that okay, S3 is catering to chunk ID 6. Now it will communicate with the map service and identify what all chunks are nearby the chunk 6. Now in our case, I'm not sure what all different chunks are there, but let's just take an example and let's just call them random numbers 3, 7 and 12. So what S3 will do is that through the gossip protocol, it will know that okay, 3 belongs to S2, 3 belongs to S2, now 7 belongs to S4 and 12 also belongs to S2. So it will send requests to both S2 and S4 that okay, I am server 3 and I want the data that what all drivers belong to 3 and 12. So S2 will get a ping that give me the list of driver who belong to 3 and 12. S4 will get a ping that give me the list of drivers belonging to chunk 7. and then based on all the drivers, we will send the pings to each one of these drivers that there is a request for a cab service, do you want to accept it or not. So in this way, the cab finder service finds the drivers who are in the vicinity and sends them the pings through WebSocket Manager. So let's move on to the next concepts. I hope it is clear what the Google Maps or the map service does, what the location service does, and now we have also covered what the cab finder service does. Now we have covered three major services which are going to be part of our Uber application: the map service, the location service, and the cab finder service. Now let's have a check at the functional requirements to see what all functional requirements we are yet to implement. I think one important chunk which is missing is the trip service. We haven't yet stored the information related to a trip, when the trip is accepted, when the trip is started, and when the trip ends. We also haven't checked at the payment service. So let's just make a note of what all services are remaining. Create profile is remaining for both the drivers. I think that is very self-explanatory. Like, we will have a profile service which will expose some of the CRUD APIs like create a profile, update profile, get profile, and delete profile. So I'm not going to explain that in detail. The profile service will take care of that. Now, show availability for the driver. It is exposed to the WebSocket server that whenever the availability is live, it will start sending pings to the location service. Now, show cabs nearby is done. Start and end location, show ETA, book cab. So we have almost covered 2 to 4. Book a cab is also done. Payment service is remaining. Rating the driver can also be done through the profile service itself. So for that, we are not going to expose a different API. Like for rating, we will expose a different API, but we are not going to have a rating service just to rate the driver or the user. So this rate the driver is also done. One thing we are remaining is the trip service and possibly a payment service as well. All the navigation portion related to the driver is going to be handled by the map service, and start ride and end ride, that is going to be handled by the trip service. So let's just go and understand what the trip service and the payment service will look like. I think this is empty. We can take use of this particular page. So whenever a trip is accepted, we can just have a trip service first of all. We will have the entire chunk of WebSocket servers, and we will have a load balancer, routing service, and so on. And ultimately, we will have some trips location, trip service, my bad. So whenever a ride is accepted by the driver, a new trip will be created and added to the trips database or trips table. We are not sure, we will discuss that, how we want to go ahead with it. But let's just look back at the numbers. We were having 10 million rides in a day, and there are 24 hours. So ideally, we had 100 QPS or 100 rides were getting created almost every second. So we can divide the trip service, the database of the trip service, into two parts. One which is going to store all the inactive trips or the completed trips. They can be rejected trips as well. They can be completed trips as well. Now that database is going to keep on increasing with time. That is never going to stay the same or saturate down the lane in future. So ideally, as we discussed related to the location service as well, we would want that data to be stored in a Cassandra cluster or NoSQL cluster, because it's going to grow on and on as the time increases. So we'll have a Cassandra cluster which will store the data for all the inactive trips. For the active trips, let's make a calculation how many active trips can be during any time. So 100 QPS is there. In 1 hour, we can assume that one trip lasts for 1 hour approximately, or 100 minutes, just to make the calculations a bit quicker. So approximately 100 QPS is converted into 100 minutes, and in each minute there are 60 seconds. So ideally, this is going to be in the range of 6 into 10 raised to 5. So this data can be stored in a SQL cluster because it has a higher probability of getting retrieved by the user on an active basis. So we would ideally want the read latency for that particular information as less as possible. Most likely the Cassandra service is going to get retrieved whenever we ask for some past trips or some payment information that will be covered by the payment service. But we will have a live corpus of a SQL database, and we'll store the information for all the live trips in SQL, And what we can do is we can also have a trip archiver or a cron job. This is an archiver. What this archiver will do is every 6 hours or every some X hours, it will run a cron job which will transfer the inactive trips from the SQL database or the Redis cluster to the Cassandra cluster. So in this way, the entire trip service can be configured. Now going to the payment service also, it is quite self-explanatory. It's not as complicated as the location service or the map service or the cab finder service. Whenever a trip ends, which is also notified by the trip service, whenever a trip ends, it will send a notification to the payment service to make the calculations of what amount is going to be there for that particular ride based on the distance covered. Now this trip service will have the entire ping of location data both from the user as well as the driver. Why do we need both of them when they are sitting in the same cab? In some cases, there can be fraudulent charges raised by the user to the driver, that the driver dropped the user in between. So we can configure or we can manage all of those challenges or all of those complaints by having the entire history of location pings during the course of a trip for both the user and the driver. So the trip service data is going to be quite heavy because we are going to send location pings every few seconds from both the users. So the trip service will have the location data, it will have the start location, end location, start time, end time, and all the information which is necessary for a particular trip. Whenever the trip ends, we will also have a trip status: accepted, started and ended. These three can be the trip status. Whenever the trip ends, it will send a ping to the payment service saying that, hey, this trip ID has ended. Based on the location data, calculate the kilometers traveled. Based on the start time and end time, calculate the time taken. And based on all of these information, find out what will be the price of the cab. So payment service is also almost a trivial one. I mean, not as trivial as the profile service, but this is also a trivial one. And we'll configure the payments based on this particular service. Now, if we look at the entire diagram, so over here we have added 3 more services if I'm not wrong. One is the trip service, one is the payment service. Now this payment service will also be configured with a payment gateway. It can be Stripe, it can be Razorpay or any other payment gateway feasible for the application. And lastly, the profile service. Now let us try and cover some of the ad hoc technical concepts. Let us try and cover some other ad hoc technical concepts. For example, whenever you are in a mall, you must have seen this a lot of times. Instead of a particular pickup location, there is a preferred access point. Let's say this is a campus. Okay, let me cover the example of my hostel itself. Like I was in IIIT Hyderabad, and let's say this is the map. Now there were multiple access points for the cab drivers. There was boys hostel over here. There was girls hostel somewhere here. This was the main entry gate. And this was the academics block. Now at each of these 4 locations, there were preferred access points given. Now how does Uber compute them? Now if you notice, whenever you start a ride or end a ride, we have a location ping associated with it. Now based on the aggregations of this location point over a historical time period, now it can be over a few days, it can be over a few months, we will realize that okay, these are few of the preferred access point inside the campus boundary, and then the proper nomenclature will be done for all of them, that this is the entry gate, this is the academic block pickup, this is the boys hostel, and this is the girls hostel, and so on. So based on the aggregated data, if you remember, we stored all the location data along with us, and we were confused what all different things we could do with that location data. So we can perform some sort of machine learning aggregation on top of it. We will store all the data which is present in the Cassandra clusters. It can be the trip service, it can be the location data, and so on. We will pass it to the Kafka queues, and that will be consumed by different services. It can be consumed by the machine learning fraud services. I will talk about that also. It can be consumed by the Spark Storm service as well, which will perform some analytics on top of the data that we have given. For example, the preferred access point is one such service. And then it can be consumed by map service as well. For example, if the traffic is increasing or decreasing, it can lead to price surging as well. So all of these different niche concepts related to a cab service application, this can be done on top of the data that we are storing inside our different services. So in this way, preferred access point can also be covered. Now, for example, when we're finding the potential drivers who we are going to send the pings for in order to book a cab, it is also a possibility. Let me first show you what I mean. So here's the user denoted by the red cross, and we have some drivers who are waiting for the cab service. Now there can be one such driver who is going to end their trip at a particular location near the user. So ideally we would want this particular driver who is about to complete his or her trip in a nearby location to also be considered in the potential candidates for the drivers who we can send the pings. So all of this data is done on top of machine learning, and all the data that we are storing with the trip service knows that okay, the trip is about to end, the trip with this particular trip ID and the driver ID is about to end. So we can also send the ping to this particular driver that hey, your trip is about to end, do you want to accept a new ride or not? So there is a lot of things going on behind the scene when we are searching for the drivers to book cab, when we are routing through a particular city and so on. A lot of things are done in batch mode as well after the trip has ended. For example, the preferred access point was one such thing. Now I also talked about a machine learning fraud mechanism. For example, a lot of drivers do this thing. There is some sort of an incentive. Let's say if a driver completes 10 trips, he or she is going to get 1000 rupees extra. So if the driver has just completed 9 trips, they can just book a ride with another mobile phone of theirs, and they can then complete the ride just to get that additional incentive. So all of that payments data, all the location pings that we are having, all of these data is aggregated and then used to detect any fraud if possible. So now we covered a lot of topics, lot of technical concepts which are important for the overall understanding of Uber's system design. So let's just go through them once again. So these are the 6 services that we talked about: map service, location service, cab finder service, profile service, payment service and trip service. We know the responsibilities of each of these services. Let's once go through the APIs which each of these services will cater to as well. Now these APIs, I didn't cover them in detail because it felt a bit trivial after I explained all of those technical concepts and what are the responsibilities of each of these services. So I think you can just pause the video at this moment just to have a look at the different APIs. Now one important thing which I want to highlight for this particular APIs part is that, let's say I want to delete a profile. Okay, over here I am just sending the user ID of the profile which I want to delete. I cannot delete the profile of some other user ID. That is quite an intuitive thing. So how does the service know that okay, the user ID which I have mentioned and my user ID, both of them belong to the same person or belong to the same profile? So ideally for each of these services, all of these services, there is some additional context that we are going to pass along with it, and that can be in the form of user token or some sort of an API key on top of this. So we can have a user token. Now both the drivers and the users can have this user token in order to authenticate themselves, that if you want to get a trip with this particular user ID and trip ID, the user ID should belong to you. So we can use a user token or some sort of an API key. So I deliberately missed this particular part out from this API slide so that you get an idea of authentication mechanism as well along with this. So whenever a user is logged into an application, there will be some token or API key created against them. And this is going to persist over a longer time as well. If it's an API key, the user token will get generated every time the application is opened. Now this is the entity relationship diagram. What all tables can we store in our database? We already talked about the location table, which is going to persist all the information. We have the trips table. As we talked about the start location, end location, we have the status as well. We have the location ID, which is associated with the locations table, and it's a repeated entity. You know, every 4 seconds or every 5 seconds, some location ping will come and will keep adding that location data to the trips table. Now we covered all the different services. We covered fraud detection as well. We covered maps machine learning as well and driver profiling as well. like based on the fraud detection results and based on the ratings that people have given, the users have given to the driver profiling can be changed. Now, all of the data can be transmitted live through the Kafka queues, or they can be asynchronously passed in batch mode. Along with this, just for the sake of completeness, all of these services are emitting some logs. Okay, this can be error logs, this can be just debugging logs as well. Now, all of these logs are consumed by Kafka queue, and then on top of the Elasticsearch logstash Kibana ELK, on top of this particular service, ELK service, Elasticsearch logstash Kibana, we can perform log analysis and create some visualizations as well, that okay, what was the availability, what went wrong at particular time, and lots of important graphs related to monitoring and alerting can be created on top of it. So I think this is a good part to end the particular video. Like, we have covered a lot of services, we have talked about a lot of technical concepts as well, we have talked about some machine learning concepts also, which can applied on top of the information that is transmitted from the different services. I really hope you enjoyed watching through this video where we talked about some of the most important technical concepts related to an Uber-like large-scale application. If you found this content insightful, make sure you give it a thumbs up, add your opinions and query in the comment section below, and lastly, don't forget to subscribe to Scaler's YouTube channel, and don't forget to hit the bell icon so that you never miss out on insightful content. Bye-bye.